CJ, you are live. Yeah. CJ, you're on mute.
Thank
There
you.
we go.
I guess people could read my slides. They're kind of self-descriptive. Thank you very much. Sorry. So I joined the Citadel HPC team in March. I was working on firmware packaging and environment management, which has been a blast. Previously to Citadel, I was at Lab 49, where I did a bunch of data science and Python engineering. I have a PhD from Columbia in material science, of all things, mostly specializing in streaming data processing and X-ray physics. But most of you probably know me from my work with conda-forge, where I'm a core developer and chair the bot subteam, which Michael was referencing a little bit earlier. Okay, so most packages have a bunch of versions. You know, maybe you're Bot 03 and you publish a version almost every single day of the year. But I ran into kind of an interesting situation when I was doing kind of this dependency inspection I'm going to tell you about, where I found this thing called Slugify. And Slugify just doesn't have versions. It's got 3 different implementations that all claim to be Slugify, which would be great. There are tons of things that have multiple implementations. MPI's got a bunch of implementations. Not a problem. Except that all the implementations are different implementations of different things. Now, nominally, they all do, I think, Unicode character munging, but they're completely different from each other. And so I thought that this was kind of pretty wild, that there are all these things that for Python claim to be Slugify, but actually are somewhat different. And so how do we tell which implementation and or version to use? Like, most things have multiple versions that you have to decide between, but what about implementations too? Well, okay, so versions are where we're familiar at this kind of territory where things are kind of, you have to choose between them. And really, they're the only tool that we have to constrain API changes, right? You can't say that I want this one symbol, but not this other symbol. You just say, I want Python 3.6, and kind of that's as good as it gets for you. Maybe you get a micro version and that gives you the information you need, but generally not. But versions are really inaccurate. And API breakage is purely conceptual. So many people in the Python community remember the pain that was the Python 2 to 3 migration with its API and ABI changes, and kind of was just really rough. But if all you ever cared about was that 1 + 1 = 2, and you wanted to use Python to check it, you're actually doing really great. As expected, Python 3.9 does know that 1 + 1 in fact equals 2, which hopefully doesn't come a shock to any of the data scientists out there doing numerical work. But you know what? Python 1.0.1 also happened to know that 1 + 1 = 2. I'm sensing that this might actually be a truthism of maybe like mathematics itself, that Python's just really good at expressing. But if this was all that you wanted from Python, you're golden. Like, you could still be running on Python 1 and you'd be perfectly fine. Now, the second you want to check this assertion and see if it's a Boolean true, all bets are off. Python 1 didn't have bools, which is kind of wild to me. So my hope, my aspirational idea behind this project was that version pins could be obtained from symbol inspection. And by symbol inspection, we're talking about names, call signatures, types, inheritance, module names. Pretty much, if you can assign a name to it, it's a symbol. So in this case, here's like an example symbol, actually from the autotick bot itself, because why not reuse code when you can? So the name would be migrate. It's got a signature that's got self, this thing called recipe dir, adders, and a star quargs. It's got a return type. It's got types for its various chunks of its call signature. Since this is actually not a function, it's technically a method. It also has some class inheritance that we could use to try to understand if pieces are the same or not. Okay. So in order to explore this idea, I set up symbol management and symbol exporter. So symbol management is the GitHub org. Symbol exporter is the particular code that runs this little thing. It's open source. The code is under a BSD3 clause license, if anyone's particularly interested. In terms of implementation details, this is implemented for Python, but it's not necessarily constrained to Python, as an AST walker. So we take an AST walker, we walk through the Python code, and kind of just collect all of the names of everything, right? So currently we're only working with symbol names, mostly just because time constraints. You know, you can't write everything at once. And we wanted to understand how far could we get with just the names of classes, functions, modules, constants, etc., before we actually go into the deep dive of typing or call signatures or more in-depth scoping. And so the output of all this work are two tables. First are all the symbols in an artifact. And by artifact, I specifically mean like a singular compile, for instance. Now this is all Python, so compile is a little bit wonky of an idea here, but this is more specific than a version because you could have multiple compiles of something, or you could have compiles against different architectures or with different linked libraries, and all these things are different. And so artifact is kind of the word that we're using to delineate between those. And then the inverse of that table, all artifacts that supply a particular symbol. So if I say I want NumPy, great. What are all the things that provide NumPy? Or Slugify, maybe. All right, so what does this look like in action? So nominally, you could go to the internet for all this. I'm just going to use the slides that I happen to have because I copied it from the internet. So this will be a tiny slice of the internet. But this is all available via CERN, who are kind enough to provide space on their servers to support these databases and allow me to keep adding to them, which is great. So this is the package Slugify version 1.6.5. And we can see here there's a bunch of stuff in this metadata. So, all right, there's a data model version, which is mostly for my own bookkeeping. And then there's a whole bunch of names. So Slugify, of course, provides the symbol Slugify over here. It also provides something called slugify.slugify. But if you dive a little bit deeper, you can actually see that Slugify provides this thing called main Slugify calc unwanted cars RE, but we have a bit more information about it. One, we've got the line number where this thing's defined, and that it's a function, and it's got some symbols inside of that function that it relies on. So this goes and uses a whole bunch of regex tooling to do its job. And this is super valuable information for us to keep track of, because you could ask questions like, well, where's regex used in my code base? And this finds it for you. You could ask like, well, where do I use particular pandas invocations? And this would find it for you. Of course, the maybe more punchy version of this is the inverse table. So here we've gone and said, okay, well, we'll invert the table. What are all of the artifacts that attempt to supply Slugify? Okay, well, there's Slugify. Then there's Python Slugify, a couple versions, and something called Awesome Slugify. Because why have one implementation when you can have three? So these are all of the artifacts that have been indexed by the system and provide something that you could call as import Slugify in Python. Great. But they deviate quite a bit in terms of their API. So for instance, slugify.greek is a constant that's provided by Python Slugify, but nobody else. Slugify.capital S Slugify is only provided by awesome Slugify. We could go further. All right, Slugify lowercase Slugify is provided by Slugify, Python Slugify, and awesome Slugify. So that one's at least somewhat consistent. They all have got a dot Slugify somewhere in there, but all lowercase. Uppercase is right out. But only Python Slugify ships slugify.slugify.slugify. And only awesome Slugify provides Slugify RU. I imagine all the other ones are ruining the day that they forgot that that symbol should be put in. The point here, beyond me having the ability to say Slugify a ton of times, is that with this kind of information, we could actually tell which Slugifies were different, right? You could say import Slugify, use it in your code base, and as the ecosystem maintainers, whose job it is to some extent to make certain that everything kind of works together and all the tubes are plumbed correctly, we could use this kind of tooling to understand, well, what did you really mean by Slugify? Did you mean awesome Slugify, Python Slugify, vanilla Slugify? And we can pull that out from this, which I think is pretty impressive. But we can actually start using this. And so we don't just build this database, we also audit it. And what those audits look like are this. So we actually start producing version constraints as determined by the symbols that you do or don't rely on. So previously when I said a particular Slugify function depends on regex, we could say, but those 3 regex functions were only in certain versions of Python, so we can constrain you down to those versions of Python. So this is for a project called Crochet, specifically 1.10.0. And we can see here, this is what we've produced. So these are the versions that we think are compatible based off of symbol extraction. Now I'll note that there's some discrepancy here, mostly because we haven't finished indexing everything. Turns out there's a lot of versions of Python, and indexing them is actually somewhat slow because there's a lot of it. So one of the reasons why this looks so gnarly with, well, you can be greater than 2.7.12 or less than 2.7.15, but maybe not more than that, or even worse, constrained to 3.5.1 or 3.5.2, but not 3.5.3, it's just because we maybe haven't gotten around to 3.5.3 yet in terms of indexing. But you can see that we've done a really nice job. This is what conda-forge thinks the requirements are in terms of reproducing some of the dependencies here. So for instance, okay, we agree that it needs a Python version. We agree that it needs a twisted version and a wrap version. And the twisted version that we've produced via inspection is actually compliant with what conda-forge is necessary in terms of version constraints on twisted. So I think this is particularly valuable in terms of figuring out where we are, how we are doing, and whether or not changes to the symbol extraction code actually increases our compatibility with other ecosystems like conda-forge in terms of version constraints. But we can actually go the other direction as well. So we can also propose version numbers. So for instance, I'm going to compare O.4.1 and O.4.2 of a project called TrackPy, which actually was a great help for my PhD. So props to them. And one of the reasons why I had this on the top of my head. So we can take the set of all the symbols in O.4.2 and subtract that from the set of symbols in O.4.1. And we'll note here that there are quite a few symbols different here. And so there are things like feature batch after locate, but also locate functions and a bright field ring and some utility functions here. So maybe the utility functions, maybe that's a micro version bump. But with this, we could have been able to suggest to the humans, hey, by the way, maybe this is actually a minor version bump since there's a whole bunch of functionality that we've added here. Um, And I think that's also really valuable since Semver is so difficult for humans to do. Code bases are massive. So understanding whether or not you've changed a symbol in a way that actually matters to your downstream consumers is difficult and definitely a job for machines to my mind. Of course, we can actually go the other direction as well and say, well, did we actually delete any symbols that maybe we shouldn't have gotten rid of? And thankfully, TrackFi did not. There are no symbols that were in O.4.1 that were not in O.4.2. And we can actually inspect that here. And again, maybe this serves as a warning to humans to be, hey, I noticed that you're about to do a git tag, but by the way, you deleted the symbol. Are you certain that you wanted to get rid of this and maybe not make this a major version bump? So there's a lot of future work here. And maybe part of the call to action is a call for contributions, where folks can come in and issue pull requests and help out on this project. It's a fairly generic project in the sense that the AST walker is for Python, but the data format doesn't rely on necessarily Python idioms. So you could just as easily have it start cataloging stuff for C, C++, R, what have you, so long as it's kind of got basic ideas of like modules and packages and constants and functions and such, it probably fits in this data model quite nicely. But some of the things that are on our radar for the future are function signatures. It's definitely high on our list. Handling decorators, I think is very interesting since decorators have interesting scoping rules in Python. Inheritance, understanding which classes you inherit from and how that actually changes whether or not certain methods are available to you is important because we've actually found this in some of our audits where we're like, why did we miss this function? Because it got inherited and we didn't realize it. Scoping more generally for Python, Python support. So Python's important for many reasons, but its NumPy bindings are particularly important to us so that we can really kind of close the loop on some of the machine learning stack. And of course, other languages, which I am not an expert in. So we'd love for contributors to come on and bring their knowledge of other languages to try to like grow out this work. With that, I'd like to acknowledge a bunch of people. Chris Burr and Daniel Kanyas, who were both my collaborators on this project. Special shout out to Chris for helping with getting the CERN data storage and web server for us. It has been invaluable. The HPC team for their support, Citadel, who also supported this work, and of course, all of you for listening. And with that, I'm happy to try to take any questions. You're more than welcome to try it out for yourself. We're currently on version 10 of the symbols and symbol tables, and we welcome any and all contributions.
Okay, thanks, CJ. That was a really interesting talk, especially especially for me learning another language other than Python. We have a question.
Sure.
Should Python have symbol versions or SO names like C or C++ does?
That's a great question. Maybe. I think since people access Python modules in a very scattered method where like you might only pull one function from a module, limiting it to file names, I think it might be too coarse grained, where going with a much finer grained approach, maybe on the functions themselves would be better, but also it seems like a potential burden on maintainers and users. So for instance, you go in and change a function's functionality to accept new keyword arguments, right? So Python, that's totally valid and technically not an API change, right? They're keyword arguments, they're completely optional, maybe. Do you change the function version at that point? Well, maybe, but then a whole bunch of people get broken because they were expecting one version number and not the other, but their code was completely compatible. So I think that kind of tension might put you in the camp of doing the inspection at environment creation time just to check that it's compatible at a level that maybe version numbers aren't precise enough even when they're attached to individual functions.
Thank you for that. Did you do any prior research on possible other implementations?
Yes. So actually we went through a couple iterations of this. One of the first places that we looked at were the language server protocol, since we thought that would have a lot of the information that we wanted, right? So that thing that does tab completion for PyCharm or VS Code actually should have a lot of information about what symbols you have because it's got a tab complete with them, right? And I've personally just found a lot of difficulty trying to work with those protocols and extract the information that I needed. We also took a pass at this using Jedi and to some extent Parso, because again, tab completion kind of felt like the one of the right ways to approach this problem was that people have already started thinking about this, but we had actually a lot of issues doing the extraction with Jedi. Um, I'm not exactly certain what they were. We went back and forth a bunch of times, and I kind of went through and then wrote the AST parser myself. It's by no means the most elegant piece of code. Uh, Daniel Kanyas also worked a lot on this. So yeah, I'm happy to take on other implementations though.
Okay. We have time for one more question. To what extent does this overlap with type checking? Can the info in the Py files handle this?
That's also a good question. I think there are well, one types have not been so broadly accepted in the Python community, and also there's no historical archive of types, right? So if you wanted to go back to Python 1.0, there's no types assigned to any of those things. So you'd have to maybe go and produce those yourself or try to produce them in some automated fashion. I think they're certainly complementary in terms of doing type checking. So I'd be happy to see where those overlap and see how the constraints work out. And this isn't the be all end all. I think there's a lot of room for additional human tuning, as well as this and type checking.
Okay. We're at time now. Thank you so much, CJ, for your talk. It
Yeah.
was really interesting.